Hello, a great welcome to this presentation. Here I will showcase a sample calculation report to help you to understand the procedure for the evaluation of overall rigidity of Raft plus superstructure system. This information is crucial in classifying the Raft as flexible or rigid for final analysis and design. I am very optimistic that this topic would be relevant for both structural as well as geotechnical engineers. So let us start. So here is shown the foundation plan as well as a typical section through the building. So as is clear from the plan, the overall length of the raft is 37.5 meters, whereas its width is 17.5 meters. The raft is essentially provided for an open frame structure that essentially consists of a cellar floor plus 20 stories above it. So the thickness of the raft is 1 meters. As is very clear from the section, the cellar floor height is 2.6 meters and the typical story height is 3.2 meters. And we have 6 bays of columns spaced at 6 meters, and in the transverse direction the columns are spaced at 6 meters, 4 meters and 6 meters. So what would be the approach we use for this calculation report? We first proceed for the calculation of the subsoil stiffness based on the foundation plan dimensions as well as the ES value for the soil. Next, we proceed for the evaluation of the flexural rigidity of the mat for 3 cases. In case 1, we will consider only mat foundation. In case 2, we will obtain the flexural rigidity considering the mat plus the cellar floor system. Finally, we proceed for the case 3, wherein the rigidity calculation is made considering all the 3 components, namely mat, cellar floor as well as the superstructure. Having obtained the flexural rigidity of the mat in all the 3 cases, we proceed for the calculation of the relative stiffness factor Kr in each case. And then based on the Kr values obtained for each of this case, we classify the mat based on the DIN recommendations. So let us start with the input parameters for the problem. So here is listed the basic input variables. The width of the raft B is 17.5 meters. The length of the raft LF is 37.5 meters. The thickness of the raft D is 1 meter. The height of basement walls from the raft top is taken as HW, that is 2.6 meters. The thickness of basement walls, which is provided all around the building, is taken as DW equal to 0.5 meters. The overall width of the cellar slab BCS, CS here the subscript stands for the cellar slab, it is taken as 16.5 meters. The thickness of the cellar slab DCS is 0.4 meters. The width of the floor slab in this case is exactly the same as the cellar slab. So here we identify it as FS floor slab, BFS as 16.5 meters. The thickness of the floor slab is taken as the same for all the stories, and that is the DFS is taken as 0.15 meter, which is very clear from the sketch as well. Now let us proceed for the beam and the column details. For the computation of the flexural rigidity, the number of beams considered N1 equal to 4 meters, 4 numbers. The beam sizes are the width is 0.3 meters and the overall depth is 0.6 meters. Now coming to the number of columns for the flexural rigidity calculations, N2 equal to 4. And the column sizes is taken as 0.5 meters by 0.5 meters. Accordingly, B2 is 0.5 meter and H2 is 0.5 meters. The location of the top of the cellar slab from the raft bottom LOCS is 4 meters. So the spacing of the column grids as shown on the sketch, S is equal to 6 meters. Number of column bays NB is equal to 6. Number of stories for the structure is NS is 20. And a typical story height H of 3.2 meter is considered. Now we have the modulus of elasticity for three materials. First one is for the raft material EG. It is taken as 2.1 into 10 raised to 7 kN per meter square. For the example problem, as we considered an RCC reinforced cement concrete building, its E value will be the same as that of the raft material, which is again is an RCC material. So accordingly, we have EB, that is the E value for the building material. It is same as 2.1 into 10 raised to 7. Finally, the modulus of elasticity of the soil ES is taken as 18,000 kN per meter square. So for this example problem, we have used the limits of Kr prescribed in the DIN standard DIN 4018 to classify the mat either as flexible, very elastic, or up to rigid. Fine. So let us start with our calculations for case 1. So in case 1, we know that the component that contributes the flexural rigidity is only the raft. So we proceed for the calculation of the flexural rigidity of the raft Kg. It is obtained simply using the formula E into I, that is E value for the mat material multiplied by its I value, which is obviously B d cubed by 12. We know that for this problem B is 17.5 meters and the thickness of the raft or the mat is 1 meter. Substituting these values, we obtain the flexural rigidity Kg of the raft as this value. Next, we proceed for calculating the stiffness of the soil based on the continuum model, that is Kk, that is equal to Es into Lf cubed into B. This formula was already discussed in detail in the earlier presentations. Substituting the values of the various terms, we obtain the stiffness of the soil as this value. Now we proceed for the calculation of the relative stiffness factor Kr as a ratio of the flexural rigidity of the mat to the stiffness of the soil. Substituting the values, we obtain the Kr as 0.00184. Remember that the Kr value that is reported in the DIN standard is 12 times this value. So that is identified as Kr capital D, that is 12 into Kr, that is substituting the values, we obtained as 0.0221. Now going back to the DIN recommendations, we find that this value of the stiffness factor lies between 0.02 and 0.04. Therefore, the raft can be classified as medium elastic. So we conclude that based on the calculations made, if we consider only the raft as contributing to the flexural rigidity, the relative stiffness factor would be 0.0221. So now let us proceed for case 2. So in case 2, we consider along with the raft cellar floor also contributing to the flexural rigidity of the system. So the cross section that is contributing to the flexural rigidity is shown shaded over here. As you can see that it consists of the raft, it consists of the two vertical walls, and finally also the cellar slab. So obviously we know that the flexural rigidity calculation involves computation of the area, the location of the neutral axis, computation of the moment of inertia of the entire shaded section about the neutral axis. So let us proceed for these calculations. First we start calculating the cross-sectional area of the raft cellar system. Obviously we know that the total area consists of the cross-sectional area of the raft, that is B into D, plus 2 times the area of the wall, that is 2 into HW into DW, plus the cross-sectional area of the cellar floor, that is BCS into DCS. Substituting, we obtain the area of the cross-section as 26.7 meters square. Now for the computation of the moment of inertia, we need to first locate the neutral axis for this section. So for the locating the neutral axis, we use a simple formula xs is equal to summation of AIXI divided by sigma A. So substituting the first moment of inertia of the various components about the base of the raft, we locate the neutral axis of the entire cross section as 1.49 meters measured from the raft bottom. Having located the neutral axis at a distance of 1.49 meters from the raft bottom, we are ready to proceed for the computation of the moment of inertia of the raft cellar system. Obviously, we know that the moment of inertia of the raft cellar system is mi of the raft, walls and the cellar slabs added together. And we know that the moment of inertia of a component about any axis is its own centroidal axis plus area into distance square. We use this formulation to obtain the mi of the raft cellar system. Accordingly, you will find that it consists of three components. The first component is the mi of the raft about the neutral axis, and this is the contribution made by the two vertical walls, and finally the third term contributing the effect of the cellar slab. Now, substituting all these values, we compute the moment of inertia of the raft cellar system about the neutral axis of the cross section as 57.09 meter raised to 4. Having obtained the moment of inertia, we can readily proceed to the calculation of the flexural rigidity. So, before calculating the flexural rigidity, here I want to indicate one more thing. The revised calculation of the moment of inertia shows that this value of I is equivalent to a raft thickness of D1, that is 12 is by b, that is equal to 3.4 meters. What does this mean? This means that originally we know that the raft thickness was 1 meter. And now if we include the cellar slab also into the rigidity calculation, we arrive at a rigidity that is contributed by a 3.4 meter thick slab. So you just identify the difference between these calculations. So the revised flexural rigidity of the raft now can be readily evaluated kg1 as Eg into Is and is computed, and the value is given over here. Now we proceed for the revised relative stiffness factor in case 2 as 0.0722, and finally the Kr value for the DIN standard use is 12 times this Kr1 value, that is 0.866. So using the table, we find that this value lies between 0.4 and 1, and accordingly the raft is very stiff. That means from the medium elastic we come to a classification of very stiff. Now we proceed for final case, that is a case 3, wherein the flexural rigidity calculation includes the contribution from raft, cellar slab, also from the superstructure. So now we shall start with the contribution from the typical floor slab of the structure, including these 4 beams. So the area of the floor slab system, obviously we know that it consists of the floor slab plus the 4 beam cross sections. So that is very clear from this formula. AFS is equal to BFS into DFS plus this is the number of beams into the cross section area, and this evaluates to be 3.02 meters square. Now let us proceed for locating the neutral axis of this composite section, which consists of the floor slab and the 4 beams. And this is again obtained using the same formulation. X is equal to sigma AI xi divided by sigma AI, substituting the areas as well as the location of the centroid of the various components. We calculate the location of the neutral axis of this section as 0.129 meter from the top slab, that means from the top of the slab. Having calculated the neutral axis, we are ready to proceed for the calculation of the moment of inertia of this shaded section about the neutral axis. And this is computed using the same formulation, that is the total Mi is equal to Mi of this slab floor slab plus 4 times the MI of these beams. And again we will use the same parallax theorem. Substituting the various values of the parameters, we calculate the MI of the floor slab about its neutral axis as 0.0536 meter raised to 4. Having calculated the moment of inertia of the floor slab, we can evaluate the average stiffness of the floor slab using the simple formulation K is equal to I by L. Obviously for this case, we know that the L value for the floor slab is the grid to grid distance, that is 6 meters. So we obtain the floor slab stiffness as 0.00894 meter cube. Having calculated the stiffness of the floor slab, we are ready to proceed to evaluate the stiffness of the columns. So obviously we proceed first with the calculation of the moment of inertia of the story columns as IC, that is number of columns into its moment of inertia, and that works out to be 0.0208 meter raised to 4. Now we proceed for the calculation of the average story stiffness of the upper columns, that is nothing but the moment of inertia of the column divided by the story height, and that evaluates to be 0.00651 meter cube. For this simple problem, we have assumed that the column sizes are the same throughout. Accordingly, the average story stiffness of the lower columns will be same as the upper ones, which means that for the lower columns also we arrive at the same stiffness of 0.00651 meter cube. Now having calculated the moment of inertia of the floor system, the stiffness of floor system as well as the stiffness of the columns, we can proceed for calculating the effective moment of inertia of the entire story using the formulation given by Meyerhoff in 1953. That is, IBS is equal to IFS into 1 plus KU plus KL divided by KFS plus KU plus KL into NB square. So remember that here NB stands for the number of bays. So substituting the various values, we find that the effective MI of the entire story is 1.2 meter raised to 4. Having obtained the MI for a single story, we can calculate the total MI for the entire building structure by multiplying the above value by the number of stories. Accordingly, we obtain IB as 23.97 meter raised to 4. So we have in our hand the total MI of the entire building structure, which means that we can readily evaluate the flexural rigidity of the building considering all the 20 stories. That is KB is equal to EB into IB, and that provides this value, which means that the total flexural rigidity of the raft plus cellar plus building system, that is a KG2, is KG1. KG1 is nothing but the flexural rigidity we calculated in case 2 considering the raft and the cellar system plus KB contributed, that is a flexural rigidity provided by the superstructure. So the total flexural rigidity of the system value is provided over here. Having calculated the total flexural rigidity, we can provide for or go for the calculation of the ideal moment of inertia of the entire structure. And that is nothing but it's a total flexural rigidity divided by the EB value, that is 81.06 meter raised to 4. Now let us calculate what would be the equivalent thickness of the mat that provides this entire I value of 81.06, and we found that this equivalent thickness is equal to 3.82 meters. So we conclude that if we consider the cellar plus superstructure, the original mat would now be equivalent to a mat of 3.82 meters instead of 1 meter. So having obtained the overall flexural rigidity Kg2, we can proceed for the calculation of the revised relative stiffness factor Kr2 as Kg2 divided by Kk, that's equal to 0.102. Obviously the Kr value for the DIN will be 12 times this value, that works out to be 1.23. So if we go to the classification limits as per DIN, we find that this raft as per the calculation would be rigid. Thus we find that depending on what are the components we include for the flexural rigidity calculations, the classification goes on changing. So we started with a medium elastic rigid mat, and finally we came down to a rigid calculation. That means the inclusion of the various components in the flexural rigidity calculation have got a significant impact in classifying the mat. This is very clear because in case 1 it was medium elastic, and finally in case 3 its flexural rigidity is so large that it can be classified as rigid. So that's all for this presentation. So as usual, please go ahead and subscribe. And if you have any comments, please let me know. So thank you very much and have a nice day.